In this video, we're looking at endothermic and exothermic changes, possible driving force for chemical reactions. And that term, thermic, gives you an idea that we're talking about heat, energy. Endo is always to take in, exo is always to give out. Temperature changes that accompany chemical or physical changes. In chemical reactions, the biggest thing is whether the temperature rises or falls. If it goes up, then the reactants have released energy. That means that the products have less energy than the reactants and so are more stable. If the temperature falls, then the reactants absorbed energy to form the products. Products have more energy than the reactants and so are less stable. In changes of state, exothermic processes happen when bonds form. When a liquid freezes to form a solid, or when a vapor condenses. Why? Strongest forces between particles, call them intermolecular forces, are in a solid. That's why the particles are so close together. There are no intermolecular forces in a vapor. Breaking bonds is endothermic and happens when we melt a solid or boil a liquid. First of 2 points that I think people do find off-putting. An enthalpy change. It's simply an energy change at constant pressure. We can regard enthalpy changes as changes in energy. Whenever I see that term enthalpy, I'm immediately thinking energy. Total energy is always conserved, but reactions involve transferring energy between the system and the surroundings. The temperature of a substance represents the average kinetic energy of the particles. Higher the temperature, then the higher the average kinetic energy of the particles. Reactions are either exothermic or endothermic. In an exothermic reaction, remembering that exo always means to give out, thermic, we're talking about heat. Energy transfers from the system to the surroundings. Temperature of the surroundings increases. Yes, energy is transferred to the surroundings. And we get more stable products, looking here. The energy profile for an exothermic reaction. I always look at the axes first when I look at graphs. I'm seeing my potential energy. I'm seeing my reaction coordinate. Reaction coordinate really could refer to time or the progress of a reaction, but this is what IB are using at the moment. Reactants have so much potential energy. That's in the forms of bonds in the reactant particles. Products have less in this case. Now, to go from the reactants to the products, there is an increase in energy. It's essential. What's it doing? It's called the activation energy, EA, and it refers to the bond breaking process. I have to break bonds in my reactants before I can begin to form new bonds that form the products. Delta H, delta, the Greek letter, always refers to a change in heat, negative, as energy is released. So, in an exothermic reaction, the reactants have more energy than the products, and so the products are more stable. Energy is released to the surroundings, and so the temperature rises. Again, EA represents the activation energy, the minimum, underlined in bold, the minimum energy required for a reaction to proceed. If ever we're asked to define activation energy, we must include that word minimum. Particles can have more energy than is needed when they collide, but there is a minimum, and that's the activation energy. Activation energy refers to the energy required to break bonds in the reactants. Delta H, the enthalpy change of the reaction, the amount of energy released in an exothermic reaction when reactants form products. And delta H negative refers to an exothermic reaction, negative because the particles themselves have released energy. Endothermic reactions, energy transfers from the surroundings to the system. The temperature of the surroundings decreases. Less stable products are formed, as we have here. This is for an endothermic reaction. Again, my reactants have stored potential energy. That's in the form of bonds between particles in reactant molecules, and products also have some. Products here have more than reactants. I still have activation energy, the minimum energy needed for the reaction to occur, corresponding to the energy required to break bonds in the reactants. Energy released when new bonds are formed in the products. So, in an endothermic reaction, products have more energy than the reactants. That makes the product less stable than the reactants. And the energy gained is absorbed from the surroundings, and so the temperature falls. Delta H positive indicates an endothermic reaction, meaning that the particles themselves gained energy when the reaction happened. We've used this term system. Exothermic, energy transfers from the system to the surroundings. Endothermic, energy transfers from the surroundings to the system. It refers to the reactant particles themselves. Surroundings could be a solution that particles are reacting in. At a particle level, energy is released by reactant particles as heat. We observe this as the temperature rising in an exothermic change. Example, in the neutralization reaction, hydrogen ions reacting with OH- ions to make water. Bonds are being formed. Neutralization reactions are always exothermic. The hydrogen and hydroxide ions are reactants. They are the system. That's what we mean when we say energy transferred from the system. They're in aqueous solution, we can see that by the subscripts. And the water they are dissolved in is the surroundings. The reaction is exothermic. We would observe a temperature rise in the solution as the system releases energy. If the products are more stable than the reactants, then the reaction is exothermic. A rise in the temperature of the surroundings is noticed. Forming less stable products results in an endothermic reaction. Heat is absorbed by the particles and the temperature falls. Combustion reactions are exothermic except for the combustion of nitrogen. This is a special example. I'm going into it because the IB mentions it specifically. Nitrogen and oxygen combining to make nitrogen oxide. Delta H is positive. Why? Nitrogen's in group 15 and the atoms have 5 valence electrons. They will form a triple bond. Breaking a triple bond in nitrogen requires a lot of energy. There's your activation energy. And we also have to break the double bond in oxygen. More energy is required to break bonds in the reactants than the energy released when new bonds form in the products. Conversely, that's why reactions that produce nitrogen are often used in explosives. 2 quick questions to finish off. Which statement about energy changes in bond forming or breaking is correct? Pause the video, take a minute, I'll highlight the answer. Well, bond making is exothermic. That excludes A and B. It releases energy. C is wrong. Check. Bond breaking is endothermic. Again, A and B are wrong. And absorbs energy. That makes C wrong. So my answer is D. Which processes are exothermic? 3 to choose from. I'll pause for a second. Well, when steam condenses, we're getting bonds made between particles as the vapor becomes a liquid. When ice melts, it's the other way around. We're having to put energy in to break bonds in the solid to make the liquid. 2 is wrong. That means the answer has to be B, but checking. Neutralization reactions are always exothermic. That's it for this video. If you got something out of it, please like, please subscribe. That helps me. Thank you.